right, children, on we go. Today we are going to talk about the vector equations. So vector equations of lines in R3. Okay, so we have spent, 4 years of our high school career playing with lines in R2. And now we're going to talk about lines in R3. So the first thing I want you to think about is, and really I wish we were together for this, but we aren't, so here we go. Think about what it would take, what information would I have to give you to uniquely define a line in R3? Okay, so think about what we could possibly define, what information we could have. What's the minimum suite of information that we could have to define a line in R3, to uniquely define a line in R3? Well, so what we require, so needed to uniquely define a line in R3. Now, this isn't all that complicated for a line, but this is kind of a lead-in exercise to the next thing we're going to do, and that's equations of planes in R3. So nonetheless, what do we have to uniquely define to have a line uniquely defined in R3? Well, 2 distinct points. And I'm going to say on the line, but I think that goes without saying. 2 distinct points on the line. So, envision that we had our axes in R3, and again, it's pretty hard to do this on a 2-dimensional surface. However, so I've got one point where I go, out, over, and up. There's the point. Oh, I didn't get the whatever. Here it is. So there's one point, and then we've got another point that we go back, down, and back, and so here's another point here. And what we've got there is, that is going to be sufficient information to get us a unique line in R3. So 2 distinct points on the line, that'd do it. And then the other way that we could do it is we could have a point and a direction vector. And so that harkens back to what we just did with the lines in R2. So if I gave you, here's a point out here, so let's grab a different color, whatever color this is, so here's a line, and I said, and by the way, from that line, go that direction, right? So a point, and I think about it as, an anchor point, right? And we talked about the idea that there's not really an anchor point, but nevertheless, an anchor point and a direction vector, and that's going to give us another way to think about a unique line in R3. So then let's consider what the equations are going to look like, or what different equations we have at our disposal for lines in R3. So equations. And we had different equations. When we talk about an R2, we had a vector equation, we had the parametric equations, we had symmetric equations, and then we had the Cartesian equation. So we're gonna see some similarities here, certainly. So the first one, unsurprisingly, is going to be a vector equation of a line in R3. So vector equation of an R3 line. And so it's going to look very, very similar to what we did in R2. So it's going to be x1, y1, z1, or just xyz, I guess probably just xyz would be better, is equal to x naught, y naught, z naught, plus t times, and then ABC, or I'm going to say d1, d2, d3, okay, where this is t is a member of the reals. And so what we've got here is, again, I'm gonna call this our anchor point, but we talked about the idea that, strictly speaking, it's not an anchor point. It's really a line that goes from or a vector, excuse me, that goes from the origin out to there, because we're going to add this to a direction vector over here. So this is our anchor point here. There's my anchor point. And this is, of course, our direction vector. And this is a parameter. Okay, so that's the exact same style. It's just it's ordered triples now instead of ordered pairs as what we had in R2. So nothing mysterious there. And then we can get into parametric equations, right? So parametric equations. And so it's going to be the same as we did in R2. So it's going to be x is equal to x naught plus t d1, and y is equal to y naught plus t d2, and z is equal to z naught plus t d3. And again, we still have the t as a member of the reals. So, nothing really fancy here. It's the same as what we did before. And then if you recall what we did in our two lines, it's going to be the same thing here again. We're going to talk about the symmetric equations. Symmetric equations. And if you remember from what we did last time, all we did was we took each of these equations and we solved for t, and then we said, well, that's good because this t is the same for all three of those equations. And so then we set that system equal to each other. So I'm going to do that again. So we would have x minus x naught over d1 is equal to y minus y naught over d2 is equal to z minus z naught over d3. Okay, and again, remember, and you don't really need to include this, but it's equal to t because that's exactly what we did, right? Is we solve for t in each of those things, right? So to go from here to here, we solved for t, right? So that was the step there. And I mean, in theory, you can say here is that we just, isolate the components. That's what we did to go from there to there. And then, if you remember, we also then, on our two equations, we had the Cartesian equation. We talked about two different ways. The one way that we did it is we, simply cross-multiplied and cleared out the denominator and moved everything over to one side. Well, if you look here, that's going to be problematic because we have 3 across. So I'm just going to do an aside here. So the Cartesian for R2 looked something like, so if I had, so xy is equal to 2 comma 4 plus t times 1 negative 3, so there was the vector equation, and then we had, x equals 2 plus t, and we had y equals 4 minus 3t, and then we would solve, and we'd say, all right, that means that x minus 2 theoretically over 1 is equal to y minus 4 over negative 3. And so there is our symmetric. So vector, parametric, symmetric, and then we would cross multiply and we would have negative 3 x plus 6 is equal to y minus 4. And we'd shift everything over and we'd have, actually, let's shift it that direction so that our x becomes positive. So 0 equals 3x plus y minus 10. Now, I don't remember if I pointed this out. I think I pointed this out. I hope I pointed this out. Interesting thing about Cartesian form, right? So this is the Cartesian form right here. Right? This is Cartesian. This is the coefficients on our x and our y actually form the normal vector. And I'm hopeful that we talked about that, and I'm just going to review it really quickly. So, if we think about this line in R2 that we have here, so it's got an anchor point out here of 2 and 4, right? So there's 2 and 4. And then it's got a direction vector that says go over 1 and down 3. So over 1 and down 3. So there's 1 and there's -3. And so if we had that, you can see that it's actually got a slope of -1/3, because it's got no rise over run. So that's why -3/1. Nevertheless, so that's our slope of this. So to be perpendicular to that, the perpendicular slope. So if this is the slope here, the perpendicular slope is equal to 1/3. Um, and so this is actually the normal vector. So there's my direction vector. So the direction vector is equal to 1 comma -3. And if we look at this vector down here that's formed by the coefficients, it's actually the normal vector. And the normal vector is 3 and 1. And we know that it's a normal vector because it's reciprocated, right? Like we've flipped the rise and the run, we've flipped the rise and the run, and this one would yield an overall negative, and this one would yield an overall positive. So this is a normal vector. So, all right, so you might think, well, and I don't want you to write this piece down, certainly not with the 3, because we're on 4. So if we think about Cartesian, we might then think, well, normally Cartesian in R2 looks like ax plus by plus c equals 0. So maybe we could be extensible here and say, well, maybe it's ax plus by plus cz plus d equals 0. And here's the interesting thing. This actually is a Cartesian equation of something in R3, but it is not the Cartesian equation of a line in R3, because if we think about it, theoretically, these things should form a normal. And I just want to make sure we know normal means it's perpendicular to, right? So this should, in theory, be normal to the direction vector. And maybe some of you are pondering and figuring out why that's actually sort of problematic. If I gave you a line in R3, so just envision, like hold your pencil up in front of you in any orientation that you want, and I said, okay, put a second pencil, or using your finger, put your finger so that it is normal or perpendicular to that line. There are an infinite number of different ways that we could be perpendicular, right? And so it could be perpendicular pointing straight up and down. It could be perpendicular pointing left and right. It could be, there's a whole suite of different lines that are perpendicular to any one line in R3. So Cartesian equation of lines in R3, okay, so of a line in R3, no, it doesn't exist. Okay, so this is, that's why I said I don't want you to include this one. It is not available for lines. That doesn't even look like lines, but lines, hokey flip, lines in R3, right? We don't do the Cartesian equation of a line in R3. Just doesn't happen. But as a hint, this is actually going to be the Cartesian equation of a plane in R3, but we're not quite there yet. That's for tomorrow. So these are each of the different forms that a line in R3 can be represented of as in vector form. So we have a vector equation of a line, so it's got an anchor point and a direction vector. The parametric equations, all we did is we solved for each of the components. So x is equal to x naught plus t d naught d1, right? And then to get the symmetric equations, we just solved for the parameter, and then set them equal to one another, and then we're good to go. And then there isn't actually a Cartesian equation. So let's look at some examples of how we can actually make use of this, right? So examples and implementation, I guess. So let's look at the first one. So imagine we had the following. So given the point, hey, Brianna, name 3 numbers in a row. Wow, very creative, Brina. Thank you. So given the point 5, 6, 7, and Mom, give me another point.
9.
Well, I need 3 in a row.
Oh, in a row. Sorry. 7, 8, 9.
Oh, no, 9, -2, 3.
Just pick whatever.
I did. Thank you. Not creative at all. Okay, so given the points, A is 5, 6, 7, and B is 9, -2, 3, determine the, and I'm going to say equations, because I want to do all 3, of the line through those points. Okay, so if we envision it, right? So we've got, a point on the line and another point that's on the line. And so I know for a vector equation, so that's what we're going to do first, is I'm going to do the vector equation. I know that I need it to be, x, y, z is equal to an anchor point. I'm going to call it P naught plus t times a direction vector. Well, the anchor point can be anything, right? The anchor point is any point on the line. Any point. So either of those are good choices, right? They're both eligible. Now, we're not limited to those because clearly there's an infinite number of points on this line. But those are the obvious choices. So I'm going to go with that. I'm going to say, all right, so we're going to have x, y, z is equal to, and I'm going to just choose this point arbitrarily, 5, 6, 7 plus t times, now I need a direction vector. Now, I can't just use this. That's not a direction vector. That is a point. So what I need to do is I need to find a direction vector, and the direction vector is going to be the vector that goes from one point to the other. So it could be AB, that would be perfectly valid, or alternatively, we could say D is equal to BA, right? Either one of those is perfectly fine. So if I wanted AB, I know to go from 5 to 9, I add 4. To go from 6 to -2, I go down 8. And to go from 7 to 3, I go down 4, right? So there's my direction vector. Hopefully something's jumping out at you here. Stop for a moment and think, Galbraith doesn't think we're done. Why do I not think we're done here? So take a moment. Okay, hopefully you spotted this is a direction vector, right? So this just tells me the direction I need to go. And I can go along that direction as many times as I want. Direction vectors should be in lowest terms. So I can reduce this. So if I took that vector, so I said, all right, my direction vector I found out was 4, -8, -4. There's my direction vector. Well, I could say, hey, that's the same thing as 4 times 1, -2, -1. That's my direction vector. But here's the thing. I'm going to be multiplying it by any arbitrary value. So that is an arbitrary value already. So I can just get rid of that. So what I would expect, I would only give full marks, and your professors at university will also only give full marks, I would hope, for a fully reduced direction vector. Now, had you gone the other direction, so this direction vector I just found was AB. If you did BA to get from B to A, it would have been the same direction vector. So imagine I said direction vector that I want is BA, and we found it. We said, okay, to go from 9 to 5 is -4. To go from -2 to 6 is 8. And to go from 3 to 7 is 4. And then you reduce that one. You maybe would have had -1, 2, 1. And strictly speaking, that's okay too. But notice we really want the x value to be positive. So if you had have done this calculation, you'd be like, all right, all good. I've reduced it. But what I'm going to then do is I'm going to swap it to be 1, -2, -1. And we would have ended up the same way. So it doesn't matter whether my direction vector was AB or BA. That's where it's at, right? So there we go. All good. So there we go. So we have our x, y, z is equal to those. And then I want to get my parametric form. There's my vector form. I want my parametric form now. Parametric is going to be equal to, not equal to, I'll put a colon because it's a series, we're going to have x is equal to 5 plus 4t. We're going to have y is equal to 6 minus 8t. Nope, that's not right. Let's go fix that. I'm looking at the wrong one. I was looking at the top one. Get rid of these. Right, go back here. And so it's 5 just plus t and 6 minus 2t. And z is equal to 7 minus 1t, or just minus t. Now, I actually, just for the sake of being able to more easily identify my direction vector, I'll often add the 1 coefficients in right here, but it's certainly not a necessity, but I sort of like to do that, okay? So there's my parametric form. And for the sake of saving space on this sheet, I'm going to now get my symmetric form. Okay, so symmetric. So symmetric form, to go from parametric to symmetric, we just solve for the t. So we're going to have x minus 5, and I'll put it over 1, is equal to y minus 6 over negative 2 is equal to z minus 7 over negative 1. And so there it is in the symmetric form. And as we suggested before, we can't actually get a Cartesian form of a line in R3. It doesn't work. Okay, so let's try another one. So how about I give you a different variant? How about I say, given the line, and we'll do x plus 6 over 3 equals y minus 7 over negative 2 equals, I'm just going to say z. So there it is. There's one form. That's obviously, hopefully you can spot that is the symmetric form. I would like you to determine the vector and parametric forms of this same line, please. Okay, so go ahead, just pause it, give it a whirl, and then come on back. Alrighty. So I am going to go in theory, depending on how strong you are at these things, you can jump to different forms. Yeah, it's not that bad. You can jump right to either of the forms. I'm going to go to the parametric form next. So I'm going to say this would have been x equals, the 6 would be on the other side, so it would actually end up being negative 6, and then plus 3t. And we would have had y equals 7 minus 2t. And we would have z, oh, that's a weird one, z equals, what does it equal? Well, in theory, I could change this to be z, and I'm going to just change a color here so it doesn't, confuse. So z plus 0 over 1, right? So this is going to be z equals, and I'm going to actually explicitly put it there, 0 plus t, right? So there it is. And so there it is in the parametric form. And then let's get the vector form. So I'm going to isolate this. So I'm going to get vector form now. Vector form. And the vector form is going to be, well, it's pretty easy to spot. So it's going to be x, y, and z are equal to negative 6, 7, 0, because really this forms our anchor point, right? So negative 6, 7, 0 plus t times, and then our direction vector is going to be 3, negative 2, 1. And we should really say t is a member of the reals. Okay, so there it is. Those are lines, vector equations of lines in R3. I'm going to give you some homework questions to give a whirl to. And I'm going to remind again, for those of you who are, playing along and doing your homework, which I hope is everyone, that you should, if you have any questions, by all means, lob them my way, either directly email them to me or put them up on Google Classroom, and I will address them as best I can. So homework questions are going to be on page 449, and we're going to have numbers 1, 2, 5, 6, and 9. And I hope everyone has a fan-friggin-tastic day.